Okay, in this video we want to talk about the strong nuclear force and radiation, specifically radioactive decay. Okay, so these are the topics of this particular video. And we'll start with the strong force. This is often just called the strong force. Sometimes we refer to it as the strong nuclear force, but usually when you say the strong force, we know what you're talking about. The strong nuclear force is one of the four fundamental forces in nature, and these four fundamental forces are gravity, the electromagnetic force, the strong force, and the weak force. Okay? Now, gravity we've studied in the first semester in 151. And this is the force that holds bodies together, right? So this is it's even more specific in that because the electromagnetic force can do that too. It can hold things together. But this is the force. This is the universal force of attraction. And the requirement here is that the objects contain mass. Right. Now, there are objects that don't have mass that feel the effects of gravity, but they don't experience the gravitational force, right? Um, and the electromagnetic force is light, right? So this is the things like light, charged particles, Coulomb's law, the laws that govern magnetism, and so on, right? The strong force is the force that binds nuclei together. Okay? So this is the force that binds nuclei together. And the weak force governs radioactive decay. Okay? So these are the four fundamental forces in nature that we know of. And so the strong force, right? Let's suppose we have a nucleus, and inside this nucleus, let's say that this is a sodium atom, right? Now, sodium has an atomic number of 11, okay? And so what this means is that there are 11 protons in this nucleus. Okay? There's 11 protons in this nucleus. And usually there are roughly the same amount of neutrons. And so we'll put 11 neutrons in here. Okay? So we've got our 11 neutrons, and that gives us a total mass number of 22. Okay? Now, you may be wondering, why doesn't this nucleus fly apart? According to Coulomb's law, if Coulomb's law were the end story, then remember that Coulomb's law says that the force between two charged particles is equal to Coulomb's constant times the charge on the first particle times the charge on the second particle divided by the distance between them squared. And when you're talking about atomic distances, especially the distances across nuclei, this is a very small number. Okay, this is typically on the order of maybe 10 to the negative 15 meters. Okay, the distance here between these two particles would be something on the order of 10 to the negative 15. So this is really, really small. When you divide things by a really small number, you get a pretty big number. And remember that Coulomb's constant is a big number anyway. And so the net effect is that there should be a measurable force here, right? There should be a measurable force here. And not only that, not only should the force be measurable, but the force between these two protons, here and here, should be repulsive. They should want to move away from each other. So how does this nucleus stay stable? So this is stable due to the strong force. Okay? So the strong force is a force that over short distances, i.e., the distance between individual atomic or nuclear particles, not just atomic particles, but nuclear particles, okay, over these types of short distances, the strong force kind of acts like a glue. And that glue is really strong for adjacent particles. It's less strong, say, for this particle compared to this particle. So if we wanted to talk about the electromagnetic repulsion between these two protons, when protons are on the opposite side of a somewhat large nucleus, then they can start to contribute to some instability. But in the case of small nuclei, and really sodium is a small nucleus, so even here, this isn't the best picture. What really happens here is that these particles are very densely packed in, and they're almost touching and or overlapping with each other. Okay, so this distance is very small. Okay, these particles are essentially, for our practical purposes, they would be what we would consider touching, right? You would have a proton and maybe a neutron, a proton, a neutron, proton, and so on, until I had 22 particles, and they're all crammed in here very, very tightly, so that even across the nucleus from here to here is going to be a very small distance, and the strong force is still relatively stable, right? But the point here is that this acts like a glue, and the strong force is approximately 120 times stronger than the Coulomb repulsion. Okay? It's 120 times stronger than Coulomb repulsion. So, this is why nuclei do not fly apart, even though the particles inside the nucleus are either the same charge or no charge. Now, the neutrons don't really contribute to the nuclear electromagnetic force, the Coulomb force, but they do contribute to the strong force. Okay, so when a proton and a neutron are next to each other, they're going to bond pretty much just as tightly as two protons will if they're close enough to each other, or two neutrons will. Right. So both neutrons and protons both of those particles feel the strong force. Okay, both of those particles feel the strong force, right? So there you have it. We're going to take a short break, and in the next video, we will talk about radioactive decay.